Alright, so investigations into vibration induced failures of refrigerant connectors in mobile AC units. This was a case study that was presented somewhere in 1995, and there were two key faculty members from IIT Delhi who helped close the gap. As I said, what I did not know about vibrations, analysis, resonance and all that, I learned on the job. So we had Dr. Tandon, industrial tribology, machine maintenance, so we used to call it ITMEC, short form. And Dr. K. Gupta, of course, I continue to often meet him. So the way we split this project was to get the analytical part done in IIT Delhi, and we volunteered to do the experimental part in the company, so that we could have a quick resolution. And you won't believe it, the cost of this consultancy project at that time was just 25,000 rupees. Huh? Unbelievable, right? So the failures that we were encountering were in two parts of the AC unit. One was on the suction line. So I showed you a flexible connector, a braided connector. So we would have a failure on the third bellow every time in the suction line. That was a major one. And then the discharge lines were failing as well. They were not failing as repetitively, but they were having failures. So when we started looking at the whole problem from a vibration perspective, there were two important things. One was what happens when there is shunting shock, and the second was what happens when there is resonance. So far we have been focusing more on the thermodynamic aspects of a product design. So we looked at coils, we looked at compressors, and we looked at cooling. But when we looked at real life application, then we also have to consider what happens with the rotating components and what happens due to shock from the track. So these were the two things which were simultaneously interacting with the tubes. So the track during train movement is known to have frequency of excitation between 0 and 50 hertz, with amplitude as a function of frequency given by A is equal to 25 upon F. This was something available from railway specs, as well as it was common knowledge from other countries that have looked at similar problems. So when the frequency is between 1 and 10, it is 25 upon F. When it is between 10 and 50, then it is 250 upon the square of F, the frequency. Now very large relative deflections between compressor and fixed end of the line would result in problems. And then I had to do some research and reference with other countries using hermetic compressors and railways. So one of the things I found was in an application guideline that Copeland had discovered flexibility of the compressor mounting as one of the reasons for deflection, large deflections. So to verify this, we did one experiment. So we did an experiment where we made a sub-assembly, and the sub-assembly was one part of the AC unit. So if you see the compressor here, it is connected and there was a failure happening at this place. So we just made a sub-assembly of this portion. We connected the same braided connector to the compressor, and we subjected it to repetitive shock. So there was a defense equipment which was used for validating defense units for air conditioning. We used the same one in the sub-assembly, and we had this unit lifted up and suddenly dropped repetitively with the compressor weight. And in about 2 hours of repetitive tests, we could replicate the exact same failure that we had during running of the train. So the braided connector was exactly failing at the same point, and then we had confidence. We had a means of saying that yes, we know the root cause of failures. So the way to address that was to change the mounting of the compressor. So I am going to show you the details of changing the mounting of the compressor. So this was typically how a compressor was being mounted with a flexible mounting pad, and all we did was we replaced this with metal, so that the relative movement of the compressor with respect to the rest of the unit was controlled. And then we put it to the same test, so the same bump test for the same duration, and we cleared it without any problem. So the issue then comes up, what happens to the vibrations from the unit to the coach? Rubber. Rubber. See, the intention of using rubber was that if you use it in a commercial unit, stationary application, you don't want the vibrations of the compressor to go to the building, to the foundation. So it was provided with that perspective.
It would act as a damper.
Yes, it would eliminate the transmission of vibrations from the compressor body to the frame where the compressor is mounted. So here in the railway unit, there was another mounting pad which was used between the frame of the unit and the railway coach body. So that was isolating the vibrations from the unit. So that means fans, blowers, compressors, everything. So the function was being done through another set of pads which were isolating the entire unit vibrations from the coach.
This was actually redundant, so that was the reason we placed it.
It was actually an oversight in the design that we picked up a stationary application compressor, we put it as it is, and it worked fine in a certain stretch. So the root cause, if we get to, was that the quality of track between Delhi and Bombay was very different from the quality of track between Delhi and Amritsar. So the number of shocks that the unit was being subjected to was different. And another thing we found was that while there was a spec which was there with railways, the spec, there was no way to verify that the spec actually reflected the rail vibrations. So when we took that up with RDSO, they were also considering means of verifying that. And then there is a major issue, because if you find that you're not complying to spec, then the entire warranty that different manufacturers would give to railways would end up being scrutinized. So this is something which is still unanswered. And one indirect answer that I got was later on, after this project was done and there was a contract between a German company and railways for new coaches. They introduced those units, and those units had compressor failures, and the compressor failures were inside the compressor. So there's tubing inside the compressor, there's a motor mounted on springs, and they had repetitive failures. And knowing my background, they consulted me and they asked me. So I said, look, you already have the means to do this. I mean, for me to just step in and simply look at your system and give you an input is not possible. But that meant there was a challenge. There was a challenge between what was stated on the spec, because Germans would typically test to spec and assume that the spec is covering with a requisite factor of safety the entire field condition. So it indicates that the field condition is different, may be different, but you can't say for sure unless you measure it. So this took care of one set of problems, and this did not require so much of vibration analysis as it required doing a pure mechanical verification using bump tests. So where did this knowledge on vibrations come in handy? So we did something called a rap test. So have you ever heard of a rap test? So let's say I hit this and it vibrates. So this is the closest demonstration of a rap test. So you have a tube, it has a natural frequency. To get to the natural frequency, you excite it and then leave it to vibrate, and you measure that frequency. So the discharge line failures that we were experiencing were on account of resonance. But to get there, we had to experimentally validate it and do some measurements. So this was an area which, as I said before, was something which I learned on the job. So when we had Professor Gupta and Dr. Tandon come in, they came in with the vibration measurement oscilloscopes, and we mounted those and checked different directions of vibrations. So what was the natural frequency in two perpendicular directions, and we found them to be matching with the second harmonic of the compressor excitation frequency. So are you able to read some part of this, or I will read it out for you if it is. The discharge line was tested with flexible reinforced tubing and the same geometric configuration as in failed units. Then it was tested with intermediate clamps as shown in figure 1, and I will show you the figure 1 here. So this particular connector was used also in the discharge line, which is over here. And this figure actually shows the modified units. So before this modification was done with the clamps, we had looked at this braided connector. So what we did was we put the unit exactly as is and looked at the natural frequency of excitation. And then you can see different cases where the compressor mounting is rigid. In the first two cases, there were no intermediate clamps. So some of the easy shortcut solutions without doing a vibration analysis was to just hold the pipe better, and will that result in preventing failures? And that unfortunately was not resulting in preventing failures. So these measurements indicated that the natural frequency was 85 and 107.5 for one direction, which is vertical, and then for horizontal direction we had 47, 104.5, 135.5. And then we made tests using flexible mounting of the compressor, and we found that there was a small, no, not very significant difference on the natural frequency. So the discharge line failure, it seems, was apparently not because of anything to do with the mounting. It was to do with resonance. So the first harmonic of compressor excitation and the natural frequency of the discharge line was considered as the most probable cause of failure. And then if we look at observations from 1, 2, 3 and 4, it is also clear that compressor mounting has very marginal impact on discharge line natural frequencies. Now, how many of you understand the second harmonic of the compressor excitation frequency? So the compressor motor is running at 50 hertz. So the first harmonic would lie at 50 hertz plus or minus 3 hertz, because there wouldn't be an accurate frequency on the train. And the second harmonic would be at somewhere between 90 and 100, or maybe 85 and 100. And that is what these tests were pointing to: 87.5, 101, 136, third harmonic. Now if we put in clamps, which is serial number 5 and 7, flexible mounting with the clamps, the first mode of natural frequency is well placed away from the first harmonic of the compressor excitation frequency. The second mode of natural frequency could give a resonant condition with the third harmonic of the compressor excitation frequency. So the crude method of just putting a clamp was not resulting in enough separation between the compressor excitation frequency, first harmonic, second harmonic, third harmonic, and the natural frequency of the tube. Then we had the frequency, natural frequency of the compressor. The compressor is also floating on the different mounting. So looking at this, again we find that the compressor mounting, whether we change it from flexible to rigid, we still keep the natural frequency between 16.5 and 29. So the compressor natural frequency can increase because of rigid mounting, but it is still not sufficiently away from the 0 to 20 hertz. Then the next part was, while there is vibration and there is excitation of the compressor and the lines, what is really going to happen? How strong is the impact, whether it is going to lead to failure or not? For that, we had to look at the displacement. So how far does the tube move because of these match between the natural frequency of the compressor and the natural frequency of the tubes, and the impact because of the first, second and third harmonic that is coming in because of rotating parts, primarily the compressor. So this page here gives details of what all equipment was used. So we use an accelerometer, and at that time BNK 4371 was the accelerometer that was available. The unit was put to normal operation, and a steady state overall amplitude was measured using a storage oscilloscope. Again, the model number and all that is given here. The accelerometer signal was amplified using a charge amplifier, a vibration meter, an instrumentation tape recorder. T101T was used to record the steady vibration signals. And then we had a frequency spectrum analyzer to carry out the frequency analysis. So you know the reason why I was not wanting to do vibrations, because it's so complex. Right. Was used to carry out the frequency analysis to provide information about the relative contribution of various excitation frequencies. So this, and then the spectra of those are shown in the, I'll show you in the next figures. But here we have the measurement of different displacement levels, which is RMS velocity millimeter per second on the suction line with the absorber. So we have 4 cases: rigid mounting 1 and 2, flexible mounting 3 and 4, and then the displacement direction, vertical and horizontal. And what we find is that the displacement goes up to 6 millimeters per second at the first excitation frequency, and the overall displacement is 10.3 and the maximum of 25.8. Now in table 4, the high frequency component of the response signal are not included because they were very low and they were not resulting in any significant impact on failures, which was the primary objective of the study. At 49 hertz, 45 to 49 hertz, and slightly less at the 3x, which is in the 133 hertz range. Now why is it that 3x is becoming important? So the compressor that we were using had 3 cylinders. So the third cylinder means there would be a certain vibration peak at 3x of the frequency. This again was something which was a learning. Now in the absence of any standards, the values of vibration levels have been used only for comparative purposes. The values also established that the compressor is the predominant source of excitation of the tubing. And here again, when it comes to design and when you do not have standards, we did not know what level of excitation is acceptable. We had to look at comparison and look at something which was going to make a significant improvement from our status, which was resulting in failures. So we used it more as a reference, as a guide as to what would a design change do. The choices before us were to continue using flexible absorbers, which were expensive, which were imported from a company in the US, or look at providing flexibility by design. So we took the approach of the second, which is make use of flexible copper tubing and reorient them so that the natural frequency is away from both the track excitation frequency, which is in the 0 to 20 hertz range, and the first and third harmonic of the compressor vibration, compressor excitation frequency. So which is around 50 hertz. So we look at 48 hertz more because there is a slip between the rotor and the frequency. So typically 47.5, 48 would be the first excitation frequency, and 135 or thereabout would be the third excitation frequency. And knowing that it's a 3-cylinder compressor and the data that we measured, we look at these two and stay away from natural frequencies of any tubing which comes close there, close to these numbers. So the results of measurement of the discharge line with the absorber are again given here in table 5, and I think rather than go by the specific 1x, 2x and 3x, we can look at the overall acceleration, the RMS velocity in millimeters per second, and that shows that with a status which was in field, flexible, the number 4, flexible compressor mounting, and in the horizontal direction we had 144 millimeters per second of velocity, and that was a significant high in comparison to any other reading that we have. And then we also can conclude here that change of compressor mounting leads to lower levels of vibration. So from flexible to rigid, when we look at the horizontal acceleration, it drops by almost 1/3, 144 to 57.4. So this built confidence that moving from flexible to rigid mounting of the compressor is going to cut down the displacement of the tube. And then we again did similar measurements on the compressor. So there are 7 readings here on the compressor with rigid, flexible, and then there are 3 readings where we put in a star indicating rigid with an additional clamp on top. The compressor has a height, and if shunting shock is the major cause of failure, holding the compressor on top would also reduce the vibration level or the displacement level if we were to be very specific. So vibration levels of the compressor when the unit is operating show a reduction in amplitude of vibration with rigid mounting. Additional flexible mount at the top make only a marginal difference. So there is no need for the complexity of holding it on top. And then The subassembly test details. So, I mentioned to you we did a simulation on a subassembly by lifting the unit and dropping it suddenly in our defense equipment. So, these are details of those tests. So, 68 bumps per minute, and the comparison was made between rigid and flexible. Failure after 1 hour in flexible mounting and failure identical to field failures was the part that led us to confidence that flexible mounting was indeed, and we had railways come and witness this test, so we could have their confidence that our analytical approach was leading to something which would have an impact on field. So, the intention here was that this 6-month period that we had, where we had no orders, we had to get back the railway confidence, get them to come and test the units again and have business flowing, and that actually did happen. So, there was no failure when the compressor is supported, I mean both the cases, when it is having a rigid mounting and whether or not it is supported did not make a difference. So, both cases the need for an additional mount on top was not there. So, now we look at conclusion. Rigid mounting reduces the amplitude of vibration, increases the natural frequency and reduces relative movement between compressor and lines. And then we also redesigned connectors. So, I talked to you about flexible connectors without this packless vibration absorber, and with that we also had a separation margin which was clear and established from the natural frequencies, and this is essentially showing the final design. So, in the final design we had addressed vibrations, we had addressed reducing cost, and we got back the customer confidence and we had these units in operation. However, the customer also became a little more alert to vibrations. So, the facility in Bangalore was hired to do tests to the RDSO spec. So, the unit would be put on a bed, a very large bed which is typically used for aircraft tests, and there you can excite the unit to different frequencies which can simulate both the track vibrations as well as the vibrations coming from other sources. So, the 1G, the 3G and the 0.5G transverse was all done there, and only there after that. So, the units fared well in those tests. So, that was again confirmation that the work, the analytical work that we did in terms of vibration analysis was effective. This slide is simply to show you the detail of where we had put the additional clamp on top of the compressor. So, this is the place where it was put to evaluate whether it would further reduce the vibration levels or not, and we did not find it worthwhile once we had rigid mounting at the bottom. This is just to give you an idea of what kind of channel was used at the bottom, what height, and it is the detailing, and this detailing becomes more and more critical as the application becomes demanding. So, the rigid mount, there was a question, right. So, the rubber was replaced by a rigid mount which was 40 millimeters OD, and then there was a thickness of 23 millimeters. So, that was to keep it raised above, and we just kept the usual mounting locations of the compressor. There was no change needed on the base of the channels that are used for mounting the compressors. So, with this we got back the business, and these units continue to be in service in Rajdhani and Shatabdis that run today. And there is a comprehensive RDSO spec that got evolved as we did several other things. So, while we resolved the reliability issue, there were some other things that were coming up. So, I talked to you about change in test conditions from 46 to 50. So, these trains would go at different stations, they would be standing for a fairly long duration, and you are aware of the shed which does not have a very significant separation between the top of the coach and the shade that is provided for passengers waiting. So, when these trains would stand there, the compressors would trip, and the compressors would trip and then they would reset, and they would trip and they would reset, and then sometimes they would fail, or sometimes there were complaints of no cooling. So, what was discovered was that when we have a coach, we have air coming in, and then there is hot air being discharged. Okay. So long as it is free to air with no obstruction on top, there is no problem. The moment you provide a shed, this air comes back in. So there is short cycling, and there is some robustness needed in the unit. So there is a need to change the test. So from 46, we suddenly were required to have the units deliver cooling at 50 degrees centigrade. We also, while doing all this, discovered that irrespective of this cover or not, there is also a certain amount of air that just comes back in because of the natural flow of air. So we did some redesigning to provide a small duct of about 20 millimeters just ahead of the propeller fan that would direct the flow vertically upwards. And then we had to go through the usual tests, re-optimization, and some of the tools available when you have space constraints are to increase the fin density, to play with circuiting, to optimize the circuiting better, and all those were done. While we were doing all this, the compressor manufacturer began to have issues in terms of reliability. So we address everything from a system design level, and then we see the compressor is not really suitable for mobile applications. So we increased the mean time between failures by making changes in the piping, addressing vibrations. But whatever was internal to the compressor, which was inherently a compressor designed for stationary applications, began to show up. And we could not get a single hermetically sealed compressor manufacturer to say on paper that their unit is suitable for railway application. At the same time, we have a demand where railways wants units, something like 20 units a month to be supplied consistently. So the Australian reference study that I had mentioned earlier proved handy there. They had looked at scroll compressors, and we looked at the internals of a scroll compressor. There is no flexible mounting in a scroll compressor. So we got railways to agree on doing a trial in the integral coach factory in Chennai. They agreed to install the first unit with 2 scroll compressors. So I still remember the model number of that compressor, ZR61, and while the market in India was still not using it even in stationary applications, we had put it on top of a roof of a train, and that decision proved to be a good decision because it led to more reliable operation, and then the specs slowly began to transition from reciprocating compressors to scroll compressors for railways. In between this period of proving the design, there were Danfoss compressors, so Danfoss Man-Europe compressors that were more robust. So they were considered the workhorse in stationary applications, and that was the best bet between the transition until such time that you develop confidence on scroll compressors to use it on trains. So they had spring mounts inside, but the spring mounts were durable, and they did not have, again it was a field trial that led to this observation that they would last longer, and that was our second key. So while application knowledge was helpful, the whole thing went through a lot of field learnings before this unit became acceptable in field. So I have talked to you about vibrations, talked to you about short cycling of air. I'm just trying to remember, is there something I missed? Then we talked about condensate drain. Okay, so one other thing that came up was rain. So high speed movement of train, and then there is rain. So the condenser fan motors, although they were rated IP55, they were not withstanding the velocity with which the water would hit the motors. So there was another learning phase where the motor manufacturers came in, and we had to look at shower tests that would replicate this weakness in the motor at the test level. So before the unit is shipped out of the factory, can we detect that there is a motor? And then when you do those tests, you begin to realize that it is not just a question of degree of protection. It is also a temperature variation that happens in the enclosure of the motor. Again, something you don't learn in textbooks. So when the motor is heated up, there is a lot of hot air inside, and then the compressor cycles. So the condenser fan motor and the compressor is switched off, and it cools. In that cooling process, it draws moisture with the air. So when we are looking at protection from moisture, we still are not preventing it from taking air. So there had to be motor redesign such that that was not leading to accumulation of water droplets inside the motor. So there had to be a drain for that condensate to be coming out and freely flowing. So those are other learnings, and these learnings were leading to reliability improvements, but it was a painstaking process because we were all finding out things that were not envisaged at the design stage. They were never documented. We didn't know about it. But there was a good relationship between the manufacturers. So the company I worked for was not the only manufacturer. There was a competitor, Sidwal, and then there was they're fairly open forums, and then there were problems which were there across the units. It was not restricted to a particular unit, and there were things related to service. So this good cooperation between the customer, the service units of Indian Railways, and the manufacturers led to continuous improvement. So I talked about condenser motors. Then there was corrosion. So the frame used to be made of MS. So from mild steel to stainless steel, along with the definition of a grade 304 was another change that happened. And you make a change for RDSO, it is simply one spec change. They don't want to paint it, they want SS. But at the manufacturing level, you certainly need to be prepared to weld thin sections to thick sections. You have a frame, and the entire welding apparatus needs to change, the skill level of people need to change. So all that was another thing that was a learning. And then what was all this done for, you might ask, right? So this first one, across the country, since we went up to testing temperatures of 50 degrees centigrade, so this was met. Here this weight was in the region of 600 kgs. It was almost 1/3 of the earlier unit. Noise in this particular application, because the connection is through ducts, canvas ducts between the unit and the passenger area, there never was really an issue, or people have not become sensitive enough, whatever. So this really hasn't become a core issue right now, so I would just leave it as a question mark. Power requirement, yeah. So this is something I missed. Between different manufacturers supplying the motors for condenser fan and also the transformer that was used for the control application, there was a need to revalidate things using temperature rise with pulse width modulated power supply. So while the units worked fine for end-on generation, there was something called self-generating coaches which required some changes. But finally this was addressed. So the robustness level of the motors and the control equipment was altered so that they don't overheat with the modified waveform. Okay, now efficiency, while it is a design consideration, it did not show up as a major concern. And the reason was what was being replaced was far more inefficient than the units that were being made available with the hermetic compressors. So the COP of systems with R12 and semi-hermetic compressors is far low. I don't even remember measuring it or even seeing it in the specs. So this did not show up, but today it might. If you look at new technology today, it could be a possible evolution that we can have. Controls and safety I am going to touch in a while, but this was addressed again. Life cycle, you have seen the number of things I have talked about, and maybe I missed a few small ones, but then this was also addressed. And the fact that now it has survived more than a decade, no problem there. Pull down capacity, yeah, we had never any issues on this. Heater capacity 3 kilowatt per side, so 3 kilowatt plus 3 kilowatt was what was being used by railways earlier, and based on field experience, no one really has complained about it. So this was not something investigated in great detail. An opportunity here is, can we use a heat pump? So can we cycle the refrigeration circuit so that we don't use heaters but instead use a heat pump? Not much has been done on that, and it is more to do with availability of power and size and all that. This was a acceptance criteria, so this was addressed. This I talked about 2 units and 2 circuits. This was 4 days to 4 hours. So now, are there any other requirements that we think we have not addressed? While I have been talking, did you think of any other requirement? Have you travelled and found something missing in an air-conditioned coach? One thing I miss is that if every compartment, like there are several sections in a 3-tier or 2-tier coach, if every section could have its own control, so that continuous negotiation between different occupants about what is the right temperature is done away with.
Even the person at the top will be good due to the direct.
Yes, that is another, yeah. So now I know that you're thinking. So what all we can address by design?
Similar kind of thing happens in the case of an aeroplane when you have the small vents.
Right. Yeah.
Control
So the newer aircraft have an adjustable thing. So every occupant more or less can adjust the air directed at him or her. So, yeah, but it's more like even in your car, if there are two people, one side you have sun, other side not having sun. So one easy way of adjusting is to reduce the airflow. But yeah, something which could sense temperature for the occupant and allow him his own individual setting. So some of the luxury cars today have it. So the passenger, the co-driver's seat could have its own temperature and the driver could have his own temperature. But these are again, yeah, so this is good. I mean, when we think like this, we are looking at unmet needs, and that could be the evolution of design to something else. So we haven't touched controls as yet, right? So how do we make sure that the compressor runs reliably? So there was another part of this whole unit which was called a control panel, and this control panel had the user interface. So it would have a rotary switch which would define 3 levels of cooling: low, medium and high. And this, the sensing of it was done using mercury in glass thermometers. So it turns out right now if you look at it in an area where there are a lot of sensors, electronics and all that, it seems very crude, but it turns out it is one of the very accurate means of sensing temperature. So you have mercury inside a mercury in glass thermometer, but in addition to that, maybe I'll draw it again, or let's say this is the mercury inside, and we have it represent a certain temperature. So let's say 24 degrees centigrade. So there is a metal conductor which is immersed in the mercury and the point of setting. So this goes to something which is called a triggering circuit, which has some diodes and all that, and I'm right now not remembering the whole circuit, but what it does is that whenever there is contact between these two, it powers the relay, and that relay in turn energizes the compressor contactor. So this comes into the control panel, and then somewhere there is a contactor which is a 3-phase contactor, and that powers the compressor and the condenser fans. So this becomes a way of controlling. So the medium setting is 24, the high setting is 26 for comfort, and then depending on the type of coach, which is today's condition, it is either 24 on low or 22. So in first AC they keep it at 22 degrees centigrade. The time we were making these units, irrespective of whether it was for or second AC or a first AC, it was 22, 24, 26, and again for heating conditions it was 17, 19 and 21. These are conditions which were maintained. So there were 3 set of thermostats. There is one at 24, then another one at 26, and then there is another one at 22. So each of these would energize the pilot relay, and the pilot relay, depending on the rotary switch position, would control the temperature at 22 or 24 or 26. Then there was a need for some interlocks. So you always want to have make sure that the compressor runs only if there is air circulation. So to check that there is airflow, there is something called a vane relay. So this is a simple flap with a micro switch connected to it, and the micro switch gets energized when there is airflow. So when there is air flowing in, lifts the flap, and that is interlocked to the compressor contactor. So the compressor will switch on only if the vane relay is on. So this is another element of control. Now you have the air flowing At the same time there is some problem with the circuiting and or there is no refrigerant and you still want to protect the compressor. So then what do you do? So then you have a low pressure switch, and then you need to define what happens when the pressure goes low. Do you want to reset it automatically or do you want to reset it manually? So for low pressure, this switch is an auto reset type. For any reason, if the temperature has gone low, the pressure will go low and then the compressor is protected. Similarly, you could also have conditions where the condenser coil is blocked or the condenser fans are not working and you want protection. So you also have an HP switch. So the HP switch is a manual reset type. So once this trips, then someone needs to attend to the unit before it can be switched on again. And these are basically ways of ensuring a high uptime and addressing small issues like clogging of condenser coils and all that without much cost for railways. This is an evolution of the whole thing. And right now there has also been work to look at connected control panels, so that at one place a person can know what is the fault condition of different panels and that. So we've talked about control panel. Then we always will have in an electrical device the usual protections for short circuit, overload, and for that the combination used was overload relays as well as MCBs for each of the motors. And then when you look at an application like railways, different manufacturers will end up having their own layouts and component selection. So there was a need for standardization. So there would be group meetings which would result in a layout that was acceptable to all, so that in service people are used to a common interface. So we had the same size of MCBs for the condenser fan motors, for the compressors, for the blower motors and all that, and it was finally put into a spec. And maybe I can give you a glimpse of the spec. So this is the final standard that was released by RDS. So and this is available on the net. So any of you wanting to get into more detail for this can look at it. So we'll quickly scan this. So there are two hermetically sealed compressors or scroll compressors. Then these condenser connectors have all come into the spec now. U-loop copper connectors at suction and discharge of compressors. Rest or self-explanatory. Then there are capillaries, accumulators, fresh air filters. Filters, one area we didn't touch. So there was a spec developed for filters, and then we had a proposal to put in a sensor for a dirty filter, which did not get implemented at that time, and I don't know right now what is the current status, but there was an intent. It was addressed through the LP switch setting auto reset type. Then you can see all the components, most of which we have discussed. The condensate drain is referred to as drip tray. Then there are anti-vibration mounting pads required for installation of the roof mounted package unit on the structure, 6 numbers. These address separation of unit vibrations from the frame. There are a whole lot of Indian standards that are referred to for different components that are used. The whole intent being standardization. Okay, so then to address the robustness part, the max ambient temperature was also increased. So from 55 it was increased to 57, and the unit had to operate for 2 hours without tripping at 57 outdoor air condition. For addressing corrosion, again we had some specs introduced, and stainless steel actually ended up most of the corrosion problem. But as far as aluminium coils are concerned, they were replaced by copper. So the fins from aluminium were changed to copper, and there was a anti-corrosion coating of tin. So tin coated copper fins was one other robustness improvement element that was introduced in this product. Okay, then to ensure the frequencies that are encountered on the coach or in the train, there was a test to take the frequency down to 47.5 and take it up to 52.5 and ensure that no vibrations will result in failures of components. If you're interested, you will be able to see the drawings of the unit. This is the triggering circuit that I mentioned, where the signal from the thermostat, the mercury glass thermostat, is used to drive a relay. This is the detailed layout of the unit. So if you want, I will put in a link to this document that you can download from the website. And with this, I come to a close.